Now we're going to extend line integrals from 2D. We are going to extend line integrals from 2D to 3D. So in 2D, we would use this thing called time to drive the particle along any path that we want. But in 2D, we are restricted to living on the XY plane. Whereas in 3D, we can move in some sort of space. So we have an element of height. So we're moving in space here. Here, we're restricted to living on the XY plane. So here you have some sort of output, and we use the z-axis to represent the output. Whereas over in 3D we can't, because we can't use z to represent the output, because z is being used here to reference a height in 3D space. So the output, you have to imagine the output as being some sort of new, I don't know, axis, if you like. So for example, if your particle is currently here, let's say it's 2 across, 3 across, and 5 up, then it will output, I don't know, the value of, let's say, 2. So the output here is this new axis, if you like. And then if x, y, and z reference a particular point in 3D space. Whereas over here, you are living on the xy plane. Well, anyway, the line integral, we would use, well, remember, this is the output. This is the output. In 2D, we have the luxury of using the z-axis to represent the output. Whereas in 3D, we don't have that luxury, because z, the height, well, z is represented by the height in 3D space. So we don't have this luxury of using the z-axis to represent the output. Whereas in 2D, we do have the luxury of using z to represent the output. So in 2D, we have some sort of, well, this thing here is the height. So as the particle is moving along, you can put it into the function. Let's say the particle is currently here. You know the x and y location. You put it into the function, it will then jump to the surface. So this thing here represents this height here, the surface. It jumps to the surface. So therefore, this block here, you can imagine it as being the height. And then you would sum up for, well, you would sum up for a ds represents a distance along a particular path. So you would actually sum up this area here. Whereas in 3D, ds represents the distance moved along the actual path. So you can imagine this is ds here, and it's in 3D space. So it's moving along the x direction, the y direction, and it has some sort of height element to it. So in 3D, you have to take this into account. In 2D, because you're living on the xy plane, the arc length, if you like, this represents the arc length, whereas in 3D you have to take the height into account. We've seen this before, so I'm expecting you to have some sort of understanding. And then we've seen this before as well. So hang on. Hang on. So if you want to work out the integral in 2D, you would use this, which we've seen in the past, because your arc length. So this in a way represents, to work out the arc length, you have to take this into account. You have to take this into account. And then in 3D, extend it to 3D, looking at this bit here, you've got to use this in 3D. Okay, so it's the same idea, but the arc length, just bear in mind that the arc length, if you want to work out the arc length, you have to use this in 3D. Whereas if you're moving on the 2D plane, you just use this for the arc length. So hang on. So back in single calculus, the area has some sort of meaning. So for example, if you have velocity time graph, the area has some sort of meaning. It represents some sort of meaning, which is displacement. Now, with three variables, you can imagine this as being some sort of gravitational field or electric field. I don't know, but let's just imagine Earth is located right at the origin. So depending on where you are in in 3D space, gravity is stronger when it's nearer Earth, whereas if it's really far away, gravity is weaker. So that's why this vector here is smaller than if you're here. The vector here is stronger. Well, the point here is that the integral has some sort of meaning in real life. You can use this to model real life. So, for example, let's say you're trying to build a spaceship to escape Earth. Do you launch your rocket straight up, or do you launch it like this, or do you launch it like this? Well, you can use this. This integral can be used to represent real life. It can some sort of gravitational field or some sort of electric field. It has some sort of meaning. As we progress, you will learn how to interpret this in real life. Okay.